Hello and welcome to another episode of AI Talk. Today, we're diving into the fascinating world of neural networks and how they learn. If you've ever wondered how computers can recognize faces or even generate music, you're in the right place. Neural networks are like a team of workers in a factory, each one playing a part in processing information and making decisions. They start with some data, pass it through layers of neurons, and eventually produce an output. But what happens when they get things wrong? That's where the magic of learning comes in, and it's driven by something called gradient descent. In this episode, we're going to break down these concepts in a way that's easy to understand, even if you're just starting out. We'll explore how neural networks adjust and improve over time, and we'll introduce a fun problem for you to think about. By the end, you'll have a clearer picture of how these amazing systems work and why they sometimes run into challenges. So, let's get started and uncover the secrets of neural networks together. All right, let's talk about the basics of neural networks. Imagine you're looking at a really complex decision-making process, like recognizing a friend in a crowded photo. A neural network can help with that. But how does it work? Think of a neural network as a big network of tiny calculators called neurons. Each neuron takes in some information, does a bit of math, and then passes its result on to the next layer of neurons. This happens layer by layer, transforming the input data into something meaningful at the end. For example, in our photo, the first layer of neurons might look for simple features like edges or colors. The next layers combine these features into more complex patterns like shapes and textures. Eventually, the final layers help the network decide, hey, that's my friend's face. But here's the twist. Neural networks don't start out knowing what to look for. They learn by adjusting themselves over time. This process of learning involves figuring out where they made mistakes and then tweaking their calculations to do better next time. And this is where backpropagation comes in. Backpropagation is like a feedback loop where the network looks at its errors and makes adjustments to reduce those errors in the future. So every time the network gets something wrong, it updates its neurons to get closer to the right answer. It's a bit like how we learn from our mistakes, refining our understanding with each attempt. Now that we have a basic understanding of how neural networks process information, let's dive into one of the key methods they use to learn and improve: gradient descent. Imagine you're at the top of a hill and your goal is to get to the lowest point in the valley. But here's the catch: it's a foggy day and you can only see a few steps ahead. To find your way down, you need to take small steps in the direction that feels steepest, the direction that will take you downhill the fastest. This is exactly what gradient descent does. In the context of neural networks, gradient descent helps us minimize the error or loss that the network makes when it processes data. Each time the network makes a prediction, we can measure how far off it is from the correct answer. This difference is the error. Gradient descent calculates the gradient, which is like the slope of the hill. It tells us how steep the error is at a given point and which direction to move to decrease it. By taking steps in the direction of the steepest descent, we adjust the network's parameters to reduce the error bit by bit. Picture this process repeating over and over. Each adjustment gets us closer to the lowest point in our error landscape, where the network makes the smallest possible error. This continuous adjustment process is what allows neural networks to learn from data and improve their accuracy over time. However, just like navigating a foggy hillside, gradient descent isn't always straightforward. Sometimes it can lead us to a small dip instead of the deepest valley, or we might get stuck in a flat area where it's hard to find the right direction to go. We'll explore these challenges a bit more later. Now, let's make things a bit more concrete with a simple example to see how gradient descent works in action. We'll use a mathematical function that's easy to understand but has an interesting twist. Imagine we have a function we'll call f of x, and it's equal to x to the power of 4 minus 4 times x squared. If you plot this on a graph, it looks like a big W with two deep valleys and a peak in the middle. Our goal is to find the lowest points of this curve, the minima, using gradient descent. First, let's understand the gradient. The gradient of our function or its derivative is called f prime of x. For our function, it equals 4 times x to the power of 3 minus 8 times x. This tells us the slope of the curve at any point x. To find the minima, we take small steps in the direction where the gradient tells us to go downhill. Imagine starting at some point on the curve like x equals 1. The gradient, or f prime of 1, tells us to move left because the slope is negative there. By taking small steps in the direction indicated by the gradient, we'll move closer to the lowest point. But here's the twist. This function has more than one low point and not all of them are the same. If you start at a different point, like x equals -1, or somewhere close to the middle, your journey might be different. Think about it. Will you always end up at the lowest possible point, or could you get stuck somewhere else? Take a moment to think about this. Where do you think gradient descent will lead you if you start from different points on our curve? We'll come back to this later and reveal the answer, but for now, keep it in mind as we continue to explore the fascinating world of neural networks and gradient descent. So far, we've talked about how gradient descent helps neural networks learn by minimizing errors. But like many great things, it comes with its own set of challenges. Let's explore some of these obstacles and think about how they might impact our journey down the error hill. Firstly, one challenge is the risk of getting stuck in what's called a local minimum. Remember our function, f of x equals x to the power of 4 minus 4 times x squared? If you start near x equals 0, the gradient descent might lead you to this shallow dip rather than to the deeper valleys at x equals -2 or x equals 2. This is because the gradient or slope is 0 at x equals 0, meaning there's no slope to guide you further down. This is like finding yourself in a small pit when the real lowest point is just a bit further away. Have you ever started solving a problem and thought you found the solution, only to realize later there was a better one? That's exactly what happens with local minima. Secondly, sometimes the gradient can be too steep, leading to what's known as the exploding gradient problem. Imagine our hill had some really steep drops. If the steps you take downhill are too big, you might overshoot and end up in a completely different area. This makes learning unstable. Conversely, if the slope is too gentle, this is known as the vanishing gradient problem. Your steps might become so tiny that you hardly make any progress at all. This is like taking such small steps that you barely move downhill, making the learning process very slow. Lastly, think about the terrain itself. If the error landscape is full of bumps and twists, navigating it can be really tricky. Neural networks sometimes face these complex terrains where finding the right path to the global minimum is challenging. Given these potential issues, how do you think neural networks manage to learn effectively? Stick around because in the next section, we'll dive into some clever techniques that help overcome these hurdles and keep our learning on track. Now that we've explored some of the challenges posed by gradient descent, let's delve into how researchers and practitioners tackle these obstacles to ensure neural networks learn effectively. One effective solution is called momentum. Imagine rolling a ball down a hill. It gains momentum as it rolls, allowing it to overcome small bumps and reach a smoother path towards the bottom. Similarly, momentum in gradient descent helps smooth out fluctuations in the gradient and ensures more stable and consistent steps towards the minimum. Another technique is learning rate adaptation. This adjusts how big or small each step is in gradient descent based on how steep the slope is. Think of it like adjusting your stride when walking uphill versus downhill. You take bigger steps downhill and smaller steps uphill to maintain balance and efficiency. To combat the vanishing gradient problem, researchers have developed techniques like batch normalization and residual connections. These methods help stabilize the gradient flow during training, ensuring that even deep neural networks can effectively propagate error signals. Lastly, advancements in optimization algorithms such as ATOM and RMSprop dynamically adjust the learning rate and other parameters during training. These algorithms are designed to converge faster and more reliably compared to traditional gradient descent methods. By integrating these solutions, researchers and engineers continue to push the boundaries of what neural networks can achieve, making them more robust and efficient learners in diverse applications. As we wrap up our exploration of gradient descent in neural networks, it's clear that while this optimization method is powerful, it comes with its own set of challenges. From local minima to exploding gradients, navigating the error landscape can be daunting. However, through innovative techniques like momentum, adaptive learning rates, and advanced optimization algorithms, researchers and practitioners continue to refine gradient descent. These strategies not only mitigate common pitfalls, but also enhance the efficiency and reliability of neural network training. Whether you're just starting to delve into the world of AI or you're an experienced practitioner, understanding gradient descent is fundamental to mastering neural networks. By grasping these concepts, you empower yourself to harness the full potential of AI technologies in solving real-world problems. We hope this episode has shed light on the intricacies of gradient descent and inspired you to explore further. Before we wrap up, don't forget to listen to our AI-generated music on the podcast theme, crafted by artificial intelligence. Don't forget to subscribe to our channel, leave us your thoughts in the comments, and join us in shaping the future of AI. Thank you for listening.
through the misty trail. Steps are slow, but I won't fail. In the fog I make my way. Hope's a candle lighting gray. Slopes get steeper, edges sharp. Heartbeats race, an unseen harp. Every stumble, every fall, rising up to heed the call. Gradient descent, life unfolds, climbing high with peaks untold. Challenges will make us strong, together singing our song. Climbing through the rocky pain, every struggle not in vain. View is clearer as we rise. Storms are past, blue open skies. Even if the climb is hard, every step I won't discard. Strength and hope in every breath, journey blazing in its depth. Gradient descent, life unfolds, climbing high with peaks untold. Challenges will make us strong, together singing our song. Gradient descent, life unfolds, climbing high with peaks untold. Challenges will make us strong, together singing our song. Climbing through the rocky pain, every struggle not in vain. View is clearer as we rise. Storms are past, blue open skies. Even if the climb is hard, every step I won't discard. Strength and hope in every breath, journey blazing in its depth. Up in the AI top, where the future is now. Today, let the rhythm of progress lead you somehow. Imagine the soundscape that pulses innovation, a melody that defies all limitation. We're breaking barriers, we're pushing the line, exploring new frontiers.